Welcome back. In this last section, we are going to talk about variation. Variation is closely related to ratios and proportions. There are certain problems that we could solve using variation, or we could also solve using ratios and proportions. So it's another one of those situations where you need to do what works best for you in your problem solving skills. Let's take a look at this example. A used car company has just offered their best candidate, Nicole, a position in sales. The position offers 16% commission on her sales. Her earnings depend on the amount of her sales. For instance, if she sells a vehicle for $4,600, she will earn $736. So we can go ahead and write that in. $736. She wants to evaluate the offer but is not sure how. In this section, we will look at the relationship, such as this one, between earning sales and commission rate. So it's simply stated in here that if she sold a vehicle for $4,600, she would get $736. So her interpretation is she would earn $736 for selling a car for $4,600. How about if she sold a car for $9,200? Well, let's stick it in this formula that they graciously gave us. 9,200 times 0.16, she would earn $1,472. So she would earn $1,472 for selling a $9,200 vehicle. How about this last one? Nice expensive vehicle. So she sold a vehicle for $18,400. She gets 16%. She gets $29.44. So she would earn $29.44 for selling a vehicle for $18,400. So as the sales price increases, her earnings increase. Not only do they increase, but they increase at the same rate. If you compare 4,600 to 9,200, 9,200 is 2 times 4,600. So she also earns 2 times the rate. If she sold it for 18,400, this is 2 times 9,200. And this 29.44 is 2 times 1,472. So her selling and her earning is increasing at the same rate. Here is our formula for direct variation, and that is a perfect example of direct variation. Direct variation says that both items go up at the same rate. So our relationship is y equals k times x to the n. In this case, y is what she earned. K is our constant. K is always a constant. We call it the constant of proportionality. Very long word for such a short letter. Our K is 0.16 because every time we multiply our unit, or X, our X was the sales price. We multiplied the sales price by K and we would get Y. Now in our case, K was to the exponent of 1. There are going to be times when K is to a different exponent and your relationship is going to be exponential instead of linear. Let's take a look and see how we can figure out these direct variation problems. Identify the input X and the output Y. Determine the constant of variation, or the constant of proportionality. You may need to divide by a specified number to determine, Use the constant to write out an equation and then substitute the known values to find the unknown. That sounds like a lot, but I think after you see me do this example, it's going to be a little bit easier. So the quantity y varies directly with the cube of x. We see the words varies directly, so we can take a look up here. This is what our equation is going to kind of look like. So y, it's always going to start with y equals k. So you can pretty much write this down every single time. Y equals k times something. Well, it's going to be times x, and it says it varies directly with the cube of x, so our x is going to be cubed. So if y equals 25 when x equals 2, find y when x is 6. So the first thing we're going to do after we figure out what our equation is going to look like, we're always going to look for k next. We're going to use the values that were given to us here to find k. So we're going to plug 25 in for y equals k times x to the third, which is 2 to the third. 25 equals 8k. Divide both sides by 8, we get 25 eighths equals k. That cannot be reduced, so that is our final k. So what's our new equation? Now that we know what k is, we can actually write the actual equation that this relationship goes through. 25 over 8 times x to the third. So that's our equation. Now we have to find y when x is equal to 6. So y equals 25 eighths, because that's what we found out our k is, times 6 cubed. I am going to need my calculator for this one, so we'll multiply that out. 6 cubed times 25 divided by 8. And we get y equal to 675. And that is our final answer. Go ahead and do this example, problem 45. You will mirror exactly what I just did. Make sure you find your basic equation first, solve for k, plug your x and y values in to solve for k, write your final equation, and then plug in your x value to find y. Welcome back. Now we're going to talk about inverse variation. So water temperature in an ocean varies inversely with the water's depth. We're given the formula T for temperature equals 14,000 divided by D, our depth. That gives us the temperature in degrees Fahrenheit at a depth below the Earth's surface. Consider the Atlantic Ocean, which covers 22% of the Earth's surface. At a certain location, the depth of 500 feet, the temperature may be 28 degrees Fahrenheit. So they were nice to us in this first one. They told us at 500 feet, the temperature is 28 degrees Fahrenheit. So 500 feet deep, temp is 28 degrees Fahrenheit. That is chilly. How about at 1,000 feet? Let's see if we can figure that out. So 14,000 divided by 1,000. We can do that in our heads. We can just cut off the zeros and we get 14 over 1, or 14 degrees Fahrenheit. So at 1,000 feet deep, temp is 14 degrees Fahrenheit. How about at 2,000 degrees, or 2,000 feet? Oh, 2,000 degrees. 14,000 divided by 2,000, we get 7 degrees Fahrenheit. So at 2,000 degrees, or 2,000 feet, I keep saying degrees, deep, the temp is 7 degrees Fahrenheit. So looking at our relationships here. So 1000 is 2 times 500. However, 14 is 1/2 of 28. 2000 is 2 times 1000, whereas 7 is 1/2 of 14. So in this relationship, as the depth gets bigger, the temperature gets smaller, but it gets smaller at the same rate. So as we increase, we multiply by 2, and as the depth increases, the temperature decreases by dividing by 2. That is an inverse variation relationship. So in this relationship, you can ignore this. That somehow got copied over and shouldn't have. Y equals our constant of proportionality divided by x to the n. So let's look at these problems. These problems are going to be very similar to direct proportion or direct variation, except we're going to be using this formula instead. So quantity y varies inversely with the cube of x. If y is 25 when x is 2, find y when x is 6. So this time, a quantity y varies inversely, so k is going to still be on top, so we'll still have our y equals k, but this time the x is going to be on the bottom, and it's with the cube of x, so x is going to be cubed. So let's find our constant by plugging in these values. Y is 25, k over x to the third, so this is 25 equals k over 8, multiply both sides by 8, and we get 200 equals k. Now we can write our official formula, y equals 200 over x to the third. Now we need to find y when x is 6. So y equals 200 over 6 to the third. So let's figure that out. What is 6 to the third? 216, so 200 divided by 216 is, oh, that is quite the number, 0.925 repeating. And we're okay just writing this as a decimal. Don't feel like you have to write it as a fraction unless the question is specifically asking you to. Go ahead and work on problem 47. Pause the video and I will meet you back here for joint variation. All right, now joint variation. Joint variation occurs when a variable varies directly or inversely with multiple variables. So with joint variation, we don't have a simple little formula we can plug this into. We have to just read the problem and figure it out. However, we will still start with y equals k times something. So no matter what, with these variation problems, you're always starting with y equals k times something. Well, except in this case, because they mixed up our variables on us. So it's going to be the quantity x varies directly with the square of y equals k. Never forget that k is important. So it varies directly with the square of y, so that means multiplication. And inversely with the cube of z. Inversely means division. So that's going to be our starting formula. If x equals 6 when y equals 2 and z equals 8, find x when y equals 1 and z equals 27. Oh, and make sure you read these problems carefully. This is the cube root of z, not z cubed. I've seen a lot of people, myself included, get in trouble here. So make sure you are looking for the word root if you see cube. All right, so let's find k. We're going to plug our values in. So 6 equals k times y squared over the cube roots of z. 6 equals k times 4 over 2. 6 equals 2k. 3 equals k. So now we can write our official formula. X equals k times, not k, we just figured out what k was. X equals 3 times y squared over the cube root of z. Now we plug in our last values. They want to find x when y equals 1 and z equals 27. So x equals 3 times 1 squared over the cube root of 27. X equals 3 times 1 is 3. The cube root of 27 is 3, so x equals 1. There's our final answer. So go ahead, work on problem 29, and we can meet back here and look at our last examples. All right, let's look at some applications of direct inverse and joint variation. The distance s that an object falls varies directly with the square of its time t of the fall. If an object falls 16 feet in 1 second, how long will it fall for 144 feet? So let's look at the start of our equation. The distance s that an object falls varies directly with the square of time t. So it's going to be equal to some constant times t squared, the square of the time. So if an object falls 16 feet in 1 second, so the distance is 16 feet in 1 second, how long will it fall for 144 feet? So let's solve for k, and we get 16 equals k. That was easy enough. S equals 16 times t squared. So how long will it fall for 144 feet? So S is the distance, so 144 equals 16 times t squared. We're looking for our time. 144 divided by 16 equals, so 9 equals t squared. Take the square root of both sides, 3 equals t. Don't worry about the negative 3, we can't go backwards in time. So the answer is going to be 3 seconds. The rate of vibration of a string under constant tension varies inversely with the length of the string. If a string is 24 inches long and vibrates 128 times per second, what is the length of a string that vibrates 64 times per second? Well, let's take a look at this. The rate of vibration of a string under constant tensions, so I'm going to go with vibration, varies inversely with the length of the string, equals some constant times over the length. So that's my little cursive L. It's not great, but I just didn't want it to look like a 1. If a string is 24 inches long and vibrates for 128 times per second, so it's 24 inches long, it vibrates 128 times per second. We're going to look for our constant k so that we can figure out what length of string vibrates 64 times per second. Now, we are going to multiply both sides by 24. 3072 is k. So, our new string vibrates 64 times per second equals k over L. We're trying to find that length. So I'm going to multiply both sides by L to get rid of this fraction. Divide both sides by 64, and we get L equal to 48. So it's a 48-inch long string. There's our answer. All right, now you can work on problem 51, see how you do, and I wish you the best of luck on your homework and with the Unit 4 exam.